I know, I was trying to figure out what it had to do with the ocean as well. Um, so one of the parts of this class was actually going to be a computer vision thing because every year they usually have like a randomization aspect, but it seems that this year they don't have that, which is kind of a bummer. But the computer vision may still be useful for detecting what color sample you're picking up from the middle so that you don't accidentally pick up like the wrong color or the other teams. But that's some like advanced auto stuff. I'm not even sure if we're gonna get to that point. Alrighty, so I guess we'll go ahead and get started now. I'm gonna share my screen. Did you guys do the challenge that I said from last week for making it turn? Can I get like thumbs up or something? Any sort of feedback would be cool. All right. Um, I'm less busy this week or this next week, so I'm gonna try and figure out that Java effects problem you guys are having. I'll try and recreate it and see if I can fix it. And then I will share with you how I did that so you guys can get the simulator working. But for now, I'll just show my explanation for it and we can learn a little bit more Java too. So I think I said like A would make it turn right, like pivot right, and then B would make it turn left. So we have if-then statements, and in Java, an if-then statement is just an if, and then these parentheses, and whatever's inside the parentheses is a Boolean condition that if it's true, it'll run the code inside. So right here, we're checking gamepad1.a. This is a Boolean that returns true if the controller button A is pressed down and false if it isn't. So if it is pressed down, then we set our left power to 1 and right power to -1. So our right wheels will spin backwards, our left wheels will spin forwards. And then for B, we do the opposite. Right wheel will spin forwards, left wheel will spin backwards, and that's how you get it to pivot. And we need that after the double left power, after these are declared, because then if not, then our left stick and right stick values would just override the values that we set over here for the turning because it reads from top to bottom. Yep, there we go. All right, so that was last week's challenge. I think I'll go ahead and post that on GitHub if it all hasn't already, but it's just these like 7 lines of code, so it isn't really that much. Today we are going to do autonomous, and we're going to talk about like how you can set up an autonomous program and different ways you can get your robot moving. Our virtual robot is kind of limited in its subassemblies, so we're not going to talk about subassemblies at all, like your linear slides and your servos and stuff. Um, there's a lot of good resources online for that. We're just mainly going to be talking about how you can move the chassis with mechanism wheels and all that. So first, should I create a new program? Yeah, I'll create a new program. All right, let's create our week 2, our actually we'll call these open loop feedback autos. and I will explain what that means in a little bit. So now we need to write our extends linear op mode like we do in every single program. Let it autocorrect for us. Implement methods, the run op mode. And here we'll need to write a function called drive because we're going to be calling we're going to be calling these 4 lines of code. We're going to be writing those a lot if you don't make like a function. So if you make a function, then you can just rewrite, or you don't have to rewrite these 4 lines. So it just saves time and is more readable, in my opinion. So we're going to have to declare our variables outside the scope of this run op mode function so that our drive function down here, which is outside, will be able to utilize those variables and manipulate them. So in our class itself, we are going to call our DC motor object, and then we're going to declare 4 variables. Yep. Back right, back left, front right, front left. Okay. And we're also going to be talking about the distance sensor a little bit today. So let's call the distance sensor, let's call it focused. Okay. I'm just going to copy and paste these because it kind of gets annoying writing them. And I'm also going to copy and paste the reverse statements in there too, actually, because we need to reverse our right side motors. Otherwise, our robot will just spin. All right, it turns out I need underscores in them. Okay, and if you see our distance sensor initialization right here is exactly the same as our motor initialization, but instead of DC motor.class, it's distance sensor.class. And the name, whatever you named it in your configuration on the driver station, is whatever you're going to put here. So it's the exact same. All right, now let's make a drive function. So first, we are going to write public void. Okay, so public is a modifier that says this function can be accessed by classes that aren't the open loop feedback auto class. So any outside class in a different file can access this function. Void is saying, or whatever is after this public is saying what type of variable is going to be returned from this function. So if we want to return a number from this function, we'd write int. If we want to return a character, Boolean, all those data types. But if we don't want to return anything from this function, we'll write public void. And then our function name, which is drive. And then inside here goes what's called an argument. So arguments in Java are something that when you call a function, right now we're declaring the function. When you actually call the function and run the code in there, you can pass an argument to it and it will use that as part of its code. So we want a double, so a decimal called power, and we're going to be applying that to every single wheel. And I'm just going to copy and paste it from the other one. Okay, and now we don't have to write 4 lines of code every time. Okay. Oh yeah. So in your autonomous, the key difference from teleop is you're gonna have this wait for start like you do in teleop, but you do not have the while op mode as active unless you want it for some reason. But if you have this while mode is active, then it's just going to continue to run the code in the autonomous. So it'll just like run your autonomous as many times until the time runs out. So we don't want that to happen. We only want our autonomous to execute once. So anything after this wait for start is going to be the start of our autonomous. So the first one we're going to be talking about is time-based control, and then we're going to go to distance sensor-based control. Now, I named this class open loop feedback because there are two different types of like control methods that you can use to like navigate your robot. One is open loop feedback and one is closed loop feedback. So open loop would be the robot like just doesn't know where it is. So it's running on time. It doesn't have sensors to tell it where it's like at any certain moment. And closed loop is the robot is running based on sensor feedback. So if it goes like and it sees a wall with a distance sensor or something, it stops right in front of the wall based on the sensor reading. That's closed loop feedback. And obviously closed loop feedback is a whole lot better because it's more accurate. So that being said, we do use open loop feedback as a fallback. So last year we were running some color sensor stuff to detect the lines and then distance sensor to detect the backboard, if you guys are familiar with last year's game. But then we also had a timer in there that would kill the trajectory if it was just running too long. So like if the robot was just continuing to go for like 5 seconds, then we just stop the robot and continue with the rest of the path. So I think time-based feedback is pretty important and should be used as like a kind of failure point so that um, yeah, your robot doesn't go completely haywire, I guess, if sensors stop working. So to get a timer, we're going to use this elapsed time class, call it whatever we want. And we're going to say new elapsed time, which is going to create an elapsed time object, and it's going to start your timer right away. So we can reset the timer with the timer.reset method. And then while the timer dot seconds, this is a method that returns how many seconds has passed, elapsed on the timer so far, is less than, let's do 1.5, less than 1.5 seconds. We call our drive method, and we can pass power 0.5 to it. So if we run this code right now, it's going to drive forward at a power of 0.5 for 1.5 seconds, and then it's going to stop this while loop. So at the end of this while loop, we need to stop our motors by calling the drive function and specifying that we want our power to be 0. Let's go ahead and run that. Yeah, okay. So I forgot the thing at the top that tells us or tells the driver station that this is a program that we can run. So instead of teleop, obviously it's going to be autonomous in the tag. Let's call this um, week 2 auto, and it's in the mechanism bot group. There it is. Okay. We click start. It goes for 1.5 seconds. Perfect. Okay. So now let's talk about some closed loop feedback, which is our distance sensor. Our distance sensor will also use a while loop, and what do we call it? Front dist. This has a method called getDistance, which is going to return the distance in either inches or centimeters, and you have to specify with this argument. So if you start typing like inches in capital, then you can do that, or you can use centimeters. So while the distance is greater than, let's say, 5 inches, then we want our robot to drive. And I reversed the wrong side of wheels. So instead of going backwards now, or instead of going forwards, it goes backwards. So we're gonna have to pass a negative power into this and then kill it after that. So we go back, then we go forward. It stops at 5 inches. Perfect. So yeah, that's actually all I had today. So next week we're gonna go over encoders, motor encoders, and some more advanced navigation stuff. And then the last week we're gonna be talking about field-centric drive. Next week, we're also going to be talking about the IMU as well. So IMU used with motor encoders is what we used last year for our autonomous, and you can get a pretty robust sort of like chassis movement and navigation for that, which is pretty cool. We don't use distance sensors as much because they're kind of inaccurate and they're also slower. So you can't run your robot on full power with a distance sensor because it just doesn't refresh the values fast enough for your robot to like stop at a certain point. And that's the same for like the color sensor as well. So there was like a piece of tape on the ground and we were trying to get our robot to stop when it saw that piece of tape. And we couldn't run the robot at full power. We'd had to run it like really, really slow for it to be able to stop when it saw the tape. And that's why we use like motor encoders for longer distance traveling because it's just more accurate and it's way faster as well. Yeah, that's all I had for today. Stay on if you have any questions. Obviously, I'll try and get back to you guys about the issues you're having with the virtual robot simulator. I will send out the recording as well. This is already posted in GitHub, this program, Basic Auto Week 2. And do I have a challenge for you guys? No, not really. Play around with the simulator if you get it working. Try and take a look at these. Oh, that's cool. Take a look at these example programs and like try and figure out some stuff. But if that's all, then I'll see you guys next week.